welcome. A meeting of the series seminar, which is just slightly better attended than our usual meetings. So lots asked me to pretend as if it were a normal meeting, and I will try my best. So László Babai is our own speaker today. He graduated in 1975 from whatever, long ago. All right, what is important is that he joined University of Chicago in 1987. It was computer science department, and László joined mathematics in 1995, and he received many awards for his outstanding work, including Gödel Prize, and last year he received Donald Knuth Prize, which is one of the highest awards in our community, and he was elected as a member of the National Academy of Arts and Sciences. And we all know that graph isomorphism is one of László's lifelong passions. So, and he will talk today about the graph isomorphism, and like with any great mathematical result, it happens with last Fermat theorem, it happens with many other results. Its first announcement is followed by a period of verification that experts will have to sit and work on this result and verify it. And I just want to say that I am very proud. This activity starts here and now. It starts today, and I am very proud that it starts at our seminar. And I thank László for choosing this venue for starting all these long roads. Right. So now, without further ado, László will tell us how to solve graph isomorphism in almost polynomial time.
So thank you all for coming. As Sasha said, I am not telling you about established results. I am telling you about claims that I am making. And my hope is that you are going to poke into this and find holes where you can. So this is the beginning. I hope it's not the beginning of the end, but it is in any case, beginning of a long process before we can say that this is an established result. Okay? So I will go straight to the subject. So what is the graph isomorphism problem? Okay, I am going to abbreviate it as GI. We are given two graphs, X and Y. Those are given. And then an isomorphism between them is a bijection that preserves adjacency. And the question is, given X and Y, these are graphs, true or false that they are isomorphic. Okay, that's the decision problem. That's what we have to decide. Okay, I'm going to give you a very brief history of this, so I'm not going to dwell on the many interesting and beautiful results about it. I'm only going to mention those that in philosophically straight go to what I'm going to talk about today. So. Okay, so the method of choice for attacking the graph isomorphism problem is a combination of group theory and combinatorics. And the group theoretic method was first introduced in my paper in 1979. So group theory introduced into the subject. It was very naive group theory, but it already solved at the time a problem that later was shown to be unsolvable by purely combinatorial methods in less than exponential time. This was followed very quickly by Jean Lux's revolutionary papers that introduced group theory in far greater depths. They gave structure that permits the application of group theory to this topic in depth. Okay, so the particular result that Jean Lux proved was that if I take graphs with bounded degree, then graph isomorphism is in polynomial time. But the most important contribution is the framework that Jean Lux set up, and that is going to be the fundamental framework that I'm also going to work in. This framework in particular also led to a bound on the general complexity of the general graph isomorphism problem. This is basically a combination of Lax's group theoretic method with Zemlyachenko's observation about degree reduction. And this resulted in a complexity for the general case in exponential of O tilde of square root of n. The tilde hides polylog factors. Okay. And later in 1983, Jean Lax went into greater detail, and he was interested in reducing the polylog. So he proved that it is exponential in square root of n log n. There is a big O here. I mean, I am ignoring constants. So that is what was proved in 1983, and that result was not improved for 3 decades. So I'd like to mention one more paper that is philosophically related to this, and that's my paper with my former graduate student Paolo Codenotti on hypergraph isomorphism. If I look at hypergraphs of bounded rank, then we can get the same complexity bound as for graphs. And the methodology of that had an influence on the work that I'm going to describe now. So I should emphasize that there is a lot more to the history, and I apologize to all of those colleagues whose work I am not mentioning right here, but these are the ones that are most related to what I am trying to illustrate. Okay, before going into the details, let me mention an interesting class of graphs. They are called Johnson graphs. So a Johnson graph has V choose T vertices, where V is greater than or equal to 2T plus 1. These vertices are numbered by the T tuples of a set of V elements. So let's imagine I have a set of V elements, and out of this, I create a much bigger set of V choose T elements. The correspondence is that no matter how I pick T out of these V vertices, that will correspond to one vertex. Okay, so if this is little t, then there will be a little vertex here which I call x sub t. Okay, so that's the correspondence. Now, how do I turn this into a graph? By the following trick. If I have 2 vertices here, okay, x sub t and say x sub s, they correspond to 2 subsets, each of them having little t elements, and these two, xt and x sub s, will be adjacent if t and s differ minimally. So their difference is only 1 in every direction. So I get from t to s by removing one element and adding one more. Okay, that's this graph. So a very notable example of this is the complement of the Petersen graph. So this is J52 complement. If you take the complementary edges, this graph, the 10 vertices of this graph can be labeled by pairs of a set of 5 elements, and 2 of them are adjacent in the Petersen graph if those 2 pairs are disjoint. So in the complement, they will be adjacent if they are not disjoint, which means they share exactly 1. They differ in exactly 1 in this way. So this is Petersen's graph. And I guess no treatise or talk about graph theory could not begin with mentioning Petersen's graph right away. But now here we are talking about an infinite family of graphs. And this family of graphs has been a source of just unspeakable misery for those who wanted to do anything beyond Lax's work on graph isomorphism. And I'm going to show you why. And also I'm trying to put an end to this misery. Okay, so group theory, I said, is the method of choice here. So first of all, and the particular groups that I'm going to talk about are permutation groups. So what's a permutation group? First of all, let me give examples. I take a set omega, and this will be the permutation domain. then I have the symmetric group acting on it. That's all permutations of omega. So permutation is just a bijection of the set to itself. And so we look at all permutations of this. And now if I take a subgroup of that, okay, this less than or equal sign indicates subgroup, then that's called a permutation group, okay? A permutation group acting on the domain omega. That's a subgroup of the symmetric group. One particularly noted example of this is the alternating group. These are all even permutations. Okay, so the set of even permutations forms a subgroup. This subgroup has index 2, so it is almost as large as the entire symmetric group. So the symmetric group, if omega has n elements, then this group has order n factorial, and this group has order n factorial divided by 2. Okay, these two are I am going to refer to as the giants. Okay. So these are by far the largest permutation groups that there exist on n elements. Okay, so these are the two giants, the symmetric group and the alternating group. And, and then that distinction, whether or not I am looking at a permutation group that's one of the giants or not, that's going to be a key distinction. So the problem that I am going to, the reformulation of this problem that I am going to deal with also comes from Jean Lux's paper from 1980, and that is the string isomorphism problem. So what is a string? A string over omega would be simply a function from omega to some alphabet. Okay, so I have some finite alphabet, and to every element of omega, I assign a letter. You could think of it as assigning colors. So I'm coloring that set, but I don't want to refer to them as colors because I will have a different meaning for colors. So let's think of it as letters. So, so a string, so for instance, if this is my set of positions here, then this is a string. Okay, that's a string. Okay, now let's imagine that we in addition also have a group acting on omega. Okay, and I have not one string but two strings. Okay, so here is another string. Okay, B, C, C, and etc. All right, that's another string. And now my question is, okay, if I have look at the group elements somehow switch around my positions. They've switched the positions in this set omega. And the question is, by doing so, is it possible to transform one string to the other? Okay, so if I apply, say, sigma in G, I apply it to the string x, then that turns into a string x to the sigma by simply permuting the positions. And now the question is, so here is the question, does there exist sigma in G such that x to the sigma is equal to y? Okay, this is the question which is clearly in NP, and now we want to, so if there exists such a sigma, then we just check that it does the job, but the question is, does there exist such a sigma? So that's what we want to decide. So this is isomorphism with respect to a prescribed permutation group, and I will refer to this as G isomorphisms. And in fact, I like to write down the entire set of those isomorphisms. So iso sub G x y is the set of those sigma in G for which x to the sigma is equal to y. Okay? So that's the definition of the set that we are looking for. And then if I apply it to x and x, then I get the automorphism group. So the automorphism group of, so let me put that a little bit elsewhere. So the automorphism group with respect to G of x is simply the set of isomorphisms with respect to G of x with x. Okay? So which elements of the group if transform the string x into itself? That's the automorphism group. Now, the set of isomorphisms, this is exponentially large. So what do I mean I want to compute this set? Well, okay, it can be exponentially large, but in fact it has structure. It's either the empty set, so it is an empty set if x and y are not isomorphic, or it is a coset of the automorphism group, so it all gx times sigma, where sigma is any element of the set of isomorphisms of x and y, okay? So if I pick a particular isomorphism, then I can apply any automorphism and multiply it by that particular isomorphism, and then I get all isomorphisms. So that gives me a compact representation of the set of isomorphisms as a coset. Simply, I represent the automorphism group by a list of generators. One can do that compactly, and then just specify one isomorphism that specifies the whole set of isomorphisms. And so that's our target. Our target is that we want to determine this coset, and we are going to do that recursively. That's the now. Okay, so by definition, the automorphism group, the G automorphism group of X, is a subgroup of G. That's by definition. Okay. The question is, what happens if they are equal? Okay, so if they are equal, so if this if this is equal to this, then I claim that we are done. So if our automorphism group actually includes G, then we are done. Why is that? Because in this case, X is G isomorphic to Y if and only if X is equal to Y. Because what can G do? G transforms X to nothing other than X itself. But it is supposed to transform X to Y. Okay? So a simple comparison finishes the thing. So what is the strategy then? We make this our hypothesis. Okay? So the running hypothesis is that the automorphism group is equal to G, and we are trying to refute this. That's going to be always happening. Okay, this is my hypothesis. Let's refute it. And when I can, so if I refute this, then I can use that for aligning. I'll give an example of aligning Y with X, and then I can use that to reduce G. So this is going to be the scheme. Refute isomorphism by some invariant. That invariant somehow helps me to align Y with X, meaning that this invariant somehow will coincide. Of course, X and Y will not be equal, but what I know about them already will be. And then I reduce G using my new knowledge. Okay, so here is an example of this, a very simple example. So I look at a graph X and I look at the YG. This is now graphs, okay? I illustrate this on graphs. So I look at a graph X and I look at a graph Y, and then all I have here is, say they have V vertices, each of them. All I can say is, a priori, that they are on the same vertex set, okay? So I'm drawing two copies, but I'm imagining that that's actually the same set. So the set of vertices, which would be V, but this is the same V, same set of vertices. But now, okay, I have nothing else to go by, so I say that my group is the symmetric group acting on these V vertices. But then I discovered that some vertices have degree, I don't know, degree 3, and other vertices have degree 7, and some other vertices have degree 20. And then I look at the other side. Does the other graph have the same partition? If not, so if, for instance, if it does not have vertices of degree 3 or not the same number of them, then I already refuted isomorphism, and that's the end of it. But if they are the same number, then what I can do is, so I have this set V, and I have a partition that corresponds to X, and I have another partition that corresponds to Y. And these two partitions are isomorphic. There is a permutation that moves one partition to the other partition. Then I do that. So I changed Y, I transform it, That's what I call alignment. So now, with respect to this particular invariant, x and y are aligned. And now, once they are aligned, then, okay, I can say x and y both satisfy this picture, but then I can reduce my group. Then the automorphisms cannot move these vertices anywhere else, only to themselves. So this group is reduced to the symmetric group on V1 here times the symmetric group on V2, etc. So it's the product of the symmetric group acting on these subsets. Okay? So that's one illustration of what this alignment step and then subsequent reduction of the group means. So I keep trying to find such invariant, reduce G, and when it turns out to be impossible to reduce G anymore, then I am done. Okay, now why am I looking at the string isomorphism problem at all? Okay, the string isomorphism problem includes the graph isomorphism problem as a special case. This is a very simple observation, but this was also pointed out by Jean Lux, and so this gives a really rich field of using group theoretic methods. So what is the reduction? Well, a graph, so if G is a graph, let me call it X. I call it, the G is group, so X is the graph, okay? Then I can encode it, so if this has V vertices, I can encode it as a string of lengths n equal V choose 2. Simply for every pair, I write 0 or 1, depending on whether there is the edge is missing there or the edge is there. Okay, so if I have a graph, then for every pair of vertices, I decide, okay, I put 1 if there is an edge there, and 0 if there is no edge there. So that's n choose 2 pieces of data, and I string them up. It's a string of lengths n choose 2. That encodes the graph. And now what encodes graph isomorphism is actually the group induced. Okay, so it acts on this V choose 2, but it is induced from the symmetric group of degree V. Okay, so I have a map from the symmetric group of degree V to the symmetric group of degree V choose 2, and that induced action is the one that defines isomorphism of graphs. So two graphs are isomorphic under the symmetric group of degree V if and only if the corresponding strings are isomorphic with respect to the group. Let me give a name to that group. SV induced action on 2. Okay, so this is a subgroup of S sub V choose 2. So this is the induced action on pairs, and that of course should be familiar here, because that's exactly the automorphism group of a Johnson graph. And let me say it more generally. So a Johnson group S sub V super T, okay, it's a subgroup of S sub V choose T. It is the induced action of S sub V on T tuples. Okay? And I define similarly A sub V to the T. Okay? Analogously, the alternating group induces action. And so these two classes of groups I'm going to call Johnson groups. This is not established terminology, but Johnson graph and Johnson schemes are, and these are the automorphism groups of those schemes. So it is convenient, I guess, to call them Johnson groups. So if I look at the very special case of Johnson groups, this SV super 2, then that is what defines graph isomorphism. So that's why string isomorphism includes graph isomorphism. That's a very special case. String isomorphism requires me to find isomorphism with respect to any group, and just one particular group defines graph isomorphism. But that's the point here, that if we are stuck with that one group, then there is no way of reducing it. And here we have a rich structure the goal will be to keep reducing the group G, and that's how recurrence, to get recurrence. All this is still Jean-Lux's plan, and so let me now tell you quickly. Okay, I could spend an hour explaining Jean-Lux's algorithm, and that would be very helpful in understanding everything. But then we would run out of time, sort of. So I'm going to try to do this, juggle with this, and simply skip Jean-Lux's algorithm, which is the main tool, and go straight to, so cut for the chase. So I am immediately going to tell you what we know about the barrier cases for Lux's algorithm, okay? So Lux's algorithm works very well for certain kinds of groups, but there is a type where it stops and it is no longer efficient. Now, when I say efficient in this talk, then that means quasi-polynomial, so it means exponential in polylog. So, so this is what the barrier cases do. They have, so here is a definition. If I have a homomorphism from G to the symmetric group on some set gamma, okay, and the image G to the phi. So I write operators in the exponent, okay? So G to the phi is where phi takes G, contains the alternating group, which means that this G sub phi is one of the giants. It's either the alternating group or the symmetric group on N. Then I call this a giant homomorphism. So once again, a giant homomorphism of a group is a map into the symmetric group on some set so that the image is a giant. That's the definition. Okay? And that's where Lux's algorithm stops giving efficient reductions. Okay? So this is the barrier case. Okay? Lux's algorithm works fine as long as any such maps are restricted to very small sets gamma, for instance, bounded. As soon as they are unbounded, the algorithm doesn't immediately give polynomial time algorithm, and I am going to set the threshold to polylogarithmic. So there will be a polylogarithmic bound log n to some specific constant, and above that I say, okay, that's too big. And so that is my threshold for, as a barrier case, so gamma is greater than or equal to some polylog. However, I should mention that actually the bottleneck case for 30 years was the case when the size of gamma was square root of the number of vertices. So it was much larger than polylog, and we were not able to move forward this. So what I have now, this is the picture. The picture is that here we have this set omega, and we have a group acting on this set. But this group has a homomorphism to the symmetric group on a much smaller set. So that small set can be as small as polylogarithmic, but it causes a lot of headache when it is large, like as large as square root of the number of vertices, or even square root of the length of the string. And it is a giant homomorphism, so what we have here, this phi maps the group G onto either the alternating or the symmetric group on this gamma. So this gamma is going to be my ideal world. This gamma is not part of the domain of my string. So my string is defined on this set. This set is completely separate. Simply the existence of such a homomorphism is what we need to confront. This is where the action is going to take place. So let me tell you something about the target recurrences that will work their way to quasi-polynomial. Oh, okay, this is a good picture. So the target recurrence is going to be of this form. Suppose f of n is the amount of resources we use. Now, in this case, it will be number of group operations. So the number of group operations we use. Now, suppose that I have a recurrence of this form, that this is less than, I don't know, say n to the log n times f of 9n over 10. Suppose, okay? All right, so here I have a quasi-polynomial factor, okay? So let me call it q of n. It's quasi-polynomial. And here, what happens is a significant reduction of the domain side. Okay? So this is the typical divide and conquer idea, that I am trying to reduce the problem of size n to a moderate number of instances of a significantly smaller problem. Okay? By significantly smaller, I mean it is smaller by a constant factor, and moderate number of instances is quasi-polynomial. That's my definition. If I solve this recurrence, and let me, instead of n to the log n, just write qn, out of this it follows that fn is less than or equal to qn to the big O of log n. So what happened here is that if qn was quasi-polynomial, we just add one more log into the exponent. So if the branching factor, okay, I also refer to it, I like to refer it as the multiplicative cost of the reduction. The cost to reduce to a smaller instance might be that it is not being reduced to one instance. It is reduced to a lot of instances. The algorithm branches. This is the branching factor. That's my multiplicative cost. And then if I execute this recurrence, then I get just an extra log in the exponent. So if it was quasi-polynomial, it remains quasi-polynomial. Okay? All right. So that's our target recurrence. And the question is, how do we attempt to achieve that? Actually, if what we are able to do, I use the letter n. Letter n is the size of omega. If I am able to cut omega into two pieces, say 90%, 10%, okay, that's wonderful. That's a great reduction. But actually, what I am going to, I mean, sometimes I can do that. But what I am really targeting is cutting this. This is size m. It's a much smaller number. And I am trying to cut this into two pieces. Now, if I do that, okay, then this goes down by a factor of 9/10, but this doesn't change its size. Only when this becomes so small that it is below a specific threshold of smallness, which is going to be polylogarithmic, then I do brute force. Then I try all the elements of this symmetric group. Then I can afford that. So if m is polylogarithmic, then I can look at all permutations here, lift them up here, and do something recursively. So that's my target. But then the recurrence looks a little bit different. Then I have two parameters in this recurrence. And so what I have is I am going to measure my complexity in terms of the two parameters. One is the size of my original domain, and one is the size of this Lux barrier. And that's f and m. And then what I'm going to get is that it is less than, say, some quasi-polynomial number times fn and 9m over 10. Okay, so I'm only reducing gamma by a constant factor. Okay? Now, when it goes down all the way, gamma becomes small, then f of n and polylog, that's going to be less than let's call that also q1 times f 9/10 of n and 9/10 of n. Okay, so I have this main target for reduction, but that is going to occur only after a logarithmic number of reductions of this set. So what happens is it's easy to evaluate. Then the solution to this is, what I'm interested in is this quantity. This is going to be less than q1n times log squared then. I got two logs here. Okay? So it's still quasi-polynomial. So that is the target recurrence that we want to do. And so the goal is to reduce somehow this set. The way we are attempting to reduce this set is by, by canonical relations. Okay, so we are trying to reduce gamma by finding a canonical relation on gamma. Okay. What canonical means here and in every context that I am using is that when I say I am doing this that I have a given input string x, and I am operating on the structures associated with x. Simultaneously, I do that also for y, and what canonical means is that whatever I do carries over by isomorphisms from x to y. So, if I can find a canonical pentagon somewhere hiding in my picture here, and I cannot find that pentagon in the other one, they are not isomorphic, I reject isomorphism. If I find that canonical pentagon there also, then I am reducing the group, because then the isomorphisms of the pentagon have to be preserved by the group. So the entire symmetric group would not preserve that, so I reduce the group to the case that my canonical structure is preserved. Okay, so that's the goal. Now, question: what kind of canonical? So first of all, a canonical relation, of course, it could be a graph, for instance, and there will be a case when we find an invariant graph there, a canonical graph. But really, the goal is to get either a canonical coloring, say 10%, 90%, so no color class larger than 90%. Okay? That's a good reduction. That gives us excellent recurrence. Or a canonical partition, canonical equipartition. Now that just means that we split this up into equal classes, and I don't care how big the classes are. I only care that the classes are non-trivial, so that this is non-trivial. So the classes, the blocks of this partition are at least 2 elements, and at most n over 2. So I did split this up. That's also going to be progress. Now, why is that going to be progress? Because what I did was I reduced this entire symmetric group to the subgroup that respects this partition. Okay? So if I have, say, B blocks, okay, then they are of size m over b. And then my group went down from S sub m down to S sub m over b, Rees product S sub b. Okay, this notation is for the Rees product, and what it means I can explain in a second. It is just that I look at all permutations that permute each class separately, each block separately, independently. And after I have done that, then I just mix up the blocks. I permute the blocks. So that's a much smaller group than the original group. Actually, it is smaller by an exponential factor in M. And so that is significant progress. So these are the 2 things that I'd like to achieve. And let's suppose that I already know how to get an invariant relation. Very favorable invariant relation would be a regular graph. So suppose that I detected on gamma, and I'm only paying attention to gamma, and suppose I already detected a regular graph. This is not entirely regular, but if I join these 2, then it becomes regular. And suppose I detected a regular graph that is somehow hiding there canonically. So again, what it means to be canonical, that if I do the same thing for y, then I have to find another graph that is isomorphic to this one, and all isomorphisms between x and y. If I look at the G isomorphisms of x and y, then those must also induce an isomorphism of these. Really, these things are easiest to state in the language of categories. We are talking about functors, but let me skip that. Okay, so suppose I was lucky enough to find such a regular graph. And being regular is actually important because if a graph is regular, then in a sense it cannot have too many automorphisms, and I'm going to get into that detail in a second. So now, what I would like to do is now I want to ignore, okay, I used omega, I used the input to create this invariant relation, this canonical relation. But now, what I want to do is ignore the input and just use this invariant relation and try to use that to somehow break the symmetry. Well, this graph is regular, so I can't a priori say, okay, some vertices have different degree from others, because no, it is homogeneous. So in this case, what we do is, the classical heuristic is individualization. So I simply assign a special color to a vertex. Say this is my vertex of choice. I individualized this vertex, okay? Now the next thing is that the neighbors of this vertex notice, oh, I have a green neighbor, Okay, so let me remember that. And so being blue means I have a green neighbor, okay? Now the next thing is that this vertex is going to notice, oh, I have two blue neighbors. So then let's assign a color to that. So this gets a different color. And now this one says, oh, I have an orange neighbor, so that's going to be a new color. Let me call it this. And this one now has a blue and a green neighbor, and that's again a new thing, maybe this. And then this vertex has a neighbor that is green, this is new green, the new orange, and the old blue. So that's still something special, so maybe this. Okay, I really broke this set up into tiny pieces. Now, what was the cost of breaking them up into these tiny pieces? It's a multiplicative cost of m. What does this mean? If I do this to x, then I have to do this to every vertex of y. I have to compare them, okay? So the total set of isomorphisms between x and y was now broken into m subsets, namely those that bring this green vertex to whatever green vertex I designate here, okay? So the multiplicative cost of this individualization is, if I picked an object for individualization 1 out of m, then it is a multiplicative cost of m. So individualizing an element of an m set incurs a multiplicative cost of m, okay? And that's going to be fine as long as I make significant progress in breaking up gamma. If I individualize a vertex and I only separate it, say, square root of m of the vertices from the rest, that would not be helpful. But if I separate it 10%, then that's helpful. Then I get an excellent recurrence. Okay, so I am trying to achieve, this would be the goal, individualize a polylog number of vertices and get either a good coloring, let's say 10%, 90%, so no color class is greater than 90%, or an equipartition. Equipartition of what? Well, suppose I have a coloring, but the coloring only has 1% here, and it has 99% there. Okay, so I have an equipartition of the 99%. So that's good enough, okay? So one of these two things, this would be what I would want. The problem is that this may not be possible. There are graphs that simply don't permit this. There are graphs that are very highly resilient to this kind of partitioning, the Jones-Zone graphs. So if I take a Jones-Zone graph, JMP, okay? If I individualize less than m over, say, 10 times t vertices, then I hardly made a dent. It will be invisible. I chopped off something, and I get a similar. Okay, this graph had m choose t vertices. If I individualize some number r less than m over 10 t vertices, I get m minus r divided by choose t, which is almost the same as this number. Okay, so I didn't make progress. So Johnson graphs are obstacles to efficient partitioning. So here comes the main combinatorial theorem. Johnson graphs are the only obstacles to efficient partitioning. The exact result is the following. If X is a regular graph on m vertices, then by individualizing a polylog vertices, we can find one of the following things. A good coloring. So it's canonical. Canonical coloring with each color class being less than 90%. Okay, that's great progress. B, an equipartition, of course a non-trivial equipartition of a color class that is at least 90%, or a canonically, all of these are canonical, a canonically embedded Johnson graph on at least 90% of the vertices. John.
So to clarify, embedded doesn't mean the same adjacency relation.
Well, no, it is not a subgraph. It is something that I just noticed. It is somehow hiding there. I take on my X-ray lenses, and then I see that the graph somewhere has that canonical structure in it. So the only thing that I know about this notion of canonicity is that, okay, once I found it in X, and I found it in first input, second input, then magically, every isomorphism between these two inputs actually preserves that structure that wasn't even visible beforehand. Okay? So then the chase will be not for one of the two things that are obviously good targets, coloring or partitioning, but instead for three things. Number 1, number 2, and number 3. And let's just consider the effect of finding one or the other or the third. What is the effect on gamma of these? Okay, if I find the canonical coloring, then gamma is going to be replaced by one of the color classes than the other color classes. Now I have to say a word about Jean-Lux's algorithm. If I have a canonical coloring, then Jean-Lux's algorithm just performs a recursion that works with lightning speed. It's a linear time recursion. So we go down to this, we go down to this, we go down to this. It's a little more complicated than that because this is not on the set where the input resides. It's not on omega, so I have to work a little harder. But that's the essential idea, that I can then go reduce my gamma to gamma 1, to gamma 2, to gamma 3. Okay, so this is going to be the branching that I do, and the solution to this is going to be just simply linear. Okay, so that's the coloring. But don't forget that, okay, a coloring could be 1%, 90%, and Jean-Lux's procedure would process that at linear cost anyway. However, the amount of reduction that I would get is recurrence. The recurrence would only go down to 99%. And previously, I had to pay polylogarithmic I had to pay a quasi-polynomial branching cost. So I would not be able to recover my cost if I didn't actually get substantial reduction of the color classes. So I do this coloring where every color class is at most 90%. That's one. That reduces gamma to these sizes, and that's substantial enough reduction for the recurrence to work. The other is, okay, suppose I have an equipartition. So now in this case, the blocks of the equipartition are not going to be canonical themselves. The partition itself is canonical. So what can happen is that if I have this one, this comes from my x, this comes from my y, that has the same equipartition, but then isomorphism takes this to this, this to this, this to this, okay? So they can permute the blocks. I can't identify the block. Oh, it doesn't matter. I have B blocks, so let me just introduce a new set, 1 point for each block, and let me call that gamma prime. Now I have a group action, which is the symmetric group on this. Oh, so I reduced my gamma to at most half. Now I have a giant homomorphism into the symmetric group on gamma prime. So that's, again, phenomenal reduction, works well with the recurrence. Now what do we get out of this? If I get a Johnson graph structure, okay, so I discovered that on my gamma, I have this beautiful graph. Okay? But remember that the automorphism group of this is just, okay, so this is here now M equal some sort of V choose 2, but the automorphism group is just the symmetric group on V elements. So I am reducing gamma to a gamma prime where the size of gamma is the size of gamma prime choose T. So gamma prime is reduced to less than 1 plus twice square root of M. So that's my new M. So my M prime is less than 1 plus 2 square root of M. This is an absolutely dramatic reduction in gamma. So these Johnson graphs, they are both a curse and a blessing in this trade. It's a curse because they resist partitioning, and it's a blessing because once we found them, then we get a phenomenal reduction. So that reduction is not even quasi-polynomial. It's an n to the log n kind of reduction. So once we found this, then we are really fine. OK, so now I have to say something. Yeah, this is how we find this. So the proof of this is what I call the split or Johnson routine. That's a purely combinatorial algorithm. It has no group theory at all in it. All right, the notion of symmetric group appears in it, but not even a subgroup of that. So it is purely combinatorial, and that's going to be the subject of my talk 2 weeks from now. So now I'd like to get to the group theory. And actually, what the group theory is going to achieve is not finding an invariant graph, but it's going to find an invariant KR relation, where K is going to be something polylogarithmic. And group theory is going to be very heavily used in that search. So then I have to mention another combinatorial result, which is this. Okay, I don't know, I have X equal VR is a KR relational structure. So what this means is that this R is just a set of relations, R1, etc., R sub little r, and the R sub I are subsets of V to the power K. So they are subsets of the K-fold Cartesian product. Okay, that's a KR relational structure. And there has to be some additional condition, which I'm going to additional condition. Okay. Okay, suppose that this is the case. So this is my condition. I have a set, and I have a KR relation satisfying some condition on it. Then I can, by individualizing K minus 1 points, okay, reduce, okay, achieve goals, achieve either A or B, or find a regular graph. So that's one of the three things that I get. So the combinatorial reduction all the way through is going to be the following. We are starting from a k-ary relational structure that satisfies some condition. Then we reduce that to, either we immediately use that for partitioning. A and B means either I have a good coloring or I have an equipartition. Or if neither of these two work out, then I find a regular graph. And then I go to the split or Johnson routine that will reduce that to either partitioning or coloring or find a Johnson graph in it. So I can put these two things together and say that these k-ary relational structures, I can go all the way to either partitioning or Johnson graph. Let me tell you something about this additional condition. The additional condition is not very bad. It just says, it just rules out what is obviously would make it impossible for this to happen. And that is that if I have this set V, okay, then the automorphism group of X, okay, if the automorphism group of X contains, say, the alternating group on some set W, where W is a subset of V, okay, then it follows that W is less than or equal to, say, I don't know, say 3/4 of V. Okay, so it's 9/10 would be good enough. Okay, let me put 9/10 and then 9/10 of V. Okay, so what this means is that it is not possible. Here is my structure X. Here is the structure X. And it is not possible to arbitrarily permute 9/10 of my vertices. Doesn't sound like a terribly restrictive condition. Okay, so we are going to find such a relational structure that is not so overly symmetrical. So I call this part here the symmetry defect. Okay, so the symmetry defect is the the smallest subset so that on the complement I can do anything. And so that has to be at least 1/10. Okay? Yes, Sasha?
You mean in the group embedding, the elements, how does it act on the left side, identically or not?
Oh, identity, yes. It fixes, yes.
So
it fixes everything else and it moves around trivially.
It's a real normal embedding, not a factor of something.
However, I should mention that if it can do this and does anything here, then there is then I take the stabilizer and it still does everything here. So if this set is smaller than half, then fixing the points here cannot affect the action here.
Yeah, but taking a stabilizer is probably expensive, right?
No. Taking the stabilizer is trivial.
Okay.
Yeah. Okay. Yes, okay. One thing I didn't mention is that, of course, I'm using group theoretic algorithms, and so there is a basic theory of group theoretic algorithms that whatever you would reasonably want to do with them can be done in polynomial time. So, yeah. Okay. All right. By the way, let me mention, if you want to learn about permutation groups, to learn something that will help you understand what was going on so far, and especially what is going to go on in the next few minutes, then this is my standard reference. It is Dixon and Mortimer permutation groups. It has virtually everything about group theory that I need. Okay. So, all right. So let's then get to the group theory lemma. Oh, I really didn't want to erase this. This is going to be my standard picture. So here is going to be the, okay, so a definition. So the situation is that we have a giant homomorphism to a symmetric group. Okay? Meaning that if I take the image, then that contains, so G to the phi contains the alternating group on this set. Okay? So that's my basic assumption. Now, if this is the case, then I am going to define, so G is a G x on omega. Okay? So G is a subgroup of the symmetric group acting on omega. And now let's take X in omega. Then the stabilizer of X, denoted by G sub X, is just the subgroup consisting of those elements of G which are fixed which fix X, okay? So that's called the stabilizer subgroup. So that's a subgroup of my group. And now I can look at what happens when I restrict my homomorphism to just that subgroup, the stabilizer. And so the definition I am going to use is this may or may not be a giant homomorphism. So the image of a subgroup is a subgroup, but it could be the entire group. Nobody says that it couldn't be exactly the same as the image of the entire group. So if I have the group G here, and then here is this little subgroup G sub X, and I was mapping it into here, but it is still possible that that subgroup still maps onto. If it doesn't, then I say that X is affected by phi. So X is affected by phi if the map from Gx to Sm is not a giant. So the image does not contain the alternating group. So Gx to the phi does not contain the alternating group A sub m. That concept, the dichotomy between points that are affected and that are not, this is going to be our central divide and conquer tool. So there is a theorem here and a smaller observation. The unaffected stabilizer theorem. Okay, so let U subset omega be the set of those points in omega that are not affected. Now let me look at the group G sub parenthesis U. This is the pointwise stabilizer of U. So I fix every unaffected point. Okay? Now here is a condition. My assumption is that M is at least the max, no, it's strictly greater than the max of 8 and 2 plus base 2 log of M. M is the size of the domain. Yeah, that's here. Okay, so I have this M set on which the group acts. And that M has to be a little bit bigger than log of M. That's the condition. And under this condition, what I can say is that this map is still giant. So what I went down to is not the stabilizer of one point, but a stabilizer of a potentially very large number of points, and look at their intersection, and even that maps onto the symmetric group. Okay? So I'm going to explain the proof of this result in the group theory seminar the day after tomorrow. Yes?
It's a bit lost. Stabilizers, they are conjugated to each other, right?
Yeah, that's true. No, it's only true in an orbit.
So, which means that your action is highly intransitive, right?
Well, I mean, it doesn't need to be transitive. Yes.
No,
typically, it will be not transitive. Yes.
If it is transitive, then it cannot be that one point is affected and another is not, right?
That's true, but
okay,
then still this has a consequence.
No. Yeah.
Okay, no, this is a very important comment.
Yeah.
If the group is transitive, then either all points are affected or none of them.
Right.
But it is not possible that none of them is affected, because then my group could not be mapped onto a large group. So at least one point is affected. That's a corollary. That's an important corollary.
And which means that all of them are affected.
And then, of course, it means that all of them in the same orbit are affected. So if it's transitive, there is just one orbit, then all of them are affected. Yeah, okay? Now, I'd like to make a comment here about this condition. This condition is tight. If I permit M to be equal to 2 plus base 2 log of N, then there are infinitely many examples where none of the points is affected. So that corollary that at least one point is affected is no longer true if I allow to go down here. So there are infinitely many examples where no point is affected. Okay? So that shows you that such a condition, I mean, is unavoidable, and maybe also indicates that this is not automatic, this result. This is sort of a an elementary result. Okay, not completely elementary because it uses a consequence of the classification of finite simple groups, but it's an easily stated consequence, so it's no. Okay, but it's tight. Okay, all right. So this is what affected means, and this is what happens if I fix all the unaffected points. Okay, and then I state another one, which is lemma. This is the affected orbit lemma. Here I don't have this condition. I have the same thing, but all I am assuming that m is at least 5. And then if I look at an orbit, affected orbit means all of its elements are affected. So if delta is an affected orbit, then curl phi is not transitive on delta. Okay? So what does it mean transitive? A group is transitive if on, say, this is an orbit. Okay? So it can take every element to every element of that set. Then it's transitive. So an orbit is a set, a maximal set on which the group acts, so that it takes every element to every element. And what I'm saying is that if I look at an orbit that is affected, then if I look at what the normal subgroup that fixes every point of AM does, now this is somewhere in omega. Okay, so delta is here. Okay, and I fix every point there. That's how I get the kernel. Then I get some split here. And then there is another observation that one needs, that if I have a normal subgroup, then this is actually going to be an equipartition. So it is going to be partitioned into equal parts. Okay? So this is the kind of thing that allows us very efficient recurrence. So this means that if I fix every point there, then the set of points that are affected, those points are split up to work for recurrence, whereas the remaining points don't matter because of this. Now, this don't matter is actually, okay, let me explain something about this. Okay? So we are trying to approximate the automorphism group from above and from below. Approximating it from above is something like, okay, I find an invariant relation that limits my automorphism group. It's not yet effective because I don't know the automorphism group of that invariant relation, but I get some partition or some Johnson graph or something out of it. So I reduce the upper bound on my group. Lower bound on the automorphism group, that requires construction of automorphisms. And this is, so we are going to do some local starts. We are going to look at not the entire input, but tiny chunks of it. And out of this local start, this theorem is going to allow us to all of a sudden construct global automorphisms. And so let me try to describe this method. This is the method that I call. Okay, so this is no longer necessary. Okay, so this is the local certificates algorithm. And this is the core algorithm of the entire paper. So what I try to do is this. So here we have omega, and here we have gamma. And our assumption somehow is right now that if I know that G maps this is a giant map onto the symmetric group of gamma, symmetric or alternating. And my running hypothesis is that even the automorphism group of X, if I map that, it still maps as a giant, okay? So this is sort of the assumption, the hypothesis that now I am trying to refute. So I'm not going to try to refute something about all of G, I'm also only going to try to refute something about this projection of G onto this auxiliary set, gamma, okay? Okay, but I can't really work with this entire gamma because gamma is not small. Okay, the lower bound on gamma is quasi-polynomial, but the upper bound on gamma is square root of this. Or not even square root, it could be the entire thing. It is possible that it is almost n. But what I can do is I pick a test set. So I pick a subset A, and A is going to be quasi-polynomial. I'm going to be polylogarithmic. Okay? I pick such a set, and what I'm trying to figure out, okay, is this automorphism group at least acting as a giant on this set? Okay? So what I do is, of course, I look at the set-wise stabilizer of this set in G. That's called G sub A without parentheses. That's set-wise stabilizer. So that's a subgroup here which I can easily construct because it is just simply the lifting of what I get here, the symmetric group on A and the complement. And inside this group, I am trying to see, is it the case that inside this, that I have enough automorphisms to fill this chunk up? So I am now looking at homomorphisms to not to sim gamma, but sim A. And so here is my definition. A is full if the automorphism group, if I map the automorphism group, not in G, but in G sub A, I map that to the symmetric group of A, then this is a giant. Okay? So I say that my test set here is full if I can do anything I want inside the test set. Automorphisms can do anything inside that test set. Now, it might be a little surprising that this is a quasi-polynomial time-testable condition. So I will be able to test in polynomial and quasi-polynomial time whether or not a test set is full. And not only that, we are also going to construct useful certificates. Certificate of non-fullness. That's going to be simply a subgroup, M sub A, subgroup of the symmetric group on A, such that it is not a giant, and such that we provide a guarantee that if I look at the automorphism group in G sub A of X, then that maps, okay, so I apply phi to this, then that maps inside M of A. Not phi, but let me call this psi sub A actually, okay? So then the psi sub A image is less than M of A. So I'm encasing the automorphism group in a smaller group, okay? So here I somehow discover that if I project the automorphism group just to this set, then it's smaller than expected. And I will have an explicit subgroup there that tells me, okay, you have to stay inside that. That subgroup is going to be the first step of constructing the k-ary relations. K is going to be exactly the size of my test sets. If I have such an encasing group, that means that if I look at the ordered k tuples, they can't go everywhere. If the symmetric group acts on this, then that has k elements, so I make them an ordered set of k elements. They can go to any other ordered set of k elements. Now I have a constructive refutation of that assumption, and in fact I can tell that this k tuple can go to which k tuples. And not only here, by the way, I can compare the action on two different test sets. And I can even compare the action of a test set for x, the input x, with a test set for the input y. And I can compare them also. So I can match up what relations, what k tuples can move to what k tuples under automorphisms and under isomorphisms. So that's how this relation, k relational structure, is going to be constructed. And, and so this is the outcome, which I call a certificate of non-fullness. Now, okay, another possible outcome is fullness. So what is going to be a fullness certificate? Now there I am a little bit more, in a difficulty. So certificate of fullness that has to be a group of automorphisms, not local automorphisms. It's not something that I can control on this little test set, something that actually works for the entire input, okay? So this is, let me call it K of A. K of A is a subgroup of the automorphism group of X, well, G sub A automorphism group of X, such that K sub A itself already maps to the symmetric group on A as a giant. So I produce enough automorphisms that already certify that my subset is full. I produce enough automorphisms that already project to the symmetric or alternating group on my test set. Okay? So this is the main algorithm. The main algorithm takes a test set and then does something and eventually comes out with one of these two certificates. Either I certify that it is full or I certify that it is not. Now, okay, so what do I get here? Okay, I do the same thing also between any pair of test set. So it's not really m choose k pieces of data, m choose k, but it is m choose k squared pieces of data. And I also do it between the two inputs. So this many data, okay, each piece of data will be either an encasing subgroup or it will be some set of automorphisms and isomorphisms. Actually, automorphisms only, and that's an interesting distinction here. Usually, I can say whatever I can do with automorphisms, I can do with isomorphisms. Here, this is a glaring exception. Here, I can do something with automorphisms that I cannot do with isomorphisms, and I will need to do some extra work to infer something for isomorphisms out of that. So, namely this, okay? The certificates for non-fullness, they are local and they work for isomorphisms also, not only for automorphisms, but these will be strictly automorphism-specific things, and I don't know the interaction for these between the two inputs, the structures derived from the two inputs. Okay, so there will be a separate job to aggregate these m choose k squared times 2 data, but this is a quasi-polynomial number of things. K is polylogarithmic, so m choose k is quasi-polynomial. Okay? That's a separate group theoretic exercise to aggregate this data. But the point I'm just trying to make is that really the basic thing is to create these certificates. Once we have these certificates, then I don't worry. There are dozen ways of pushing this to a conclusion. So this is the central, this is the core piece. So let me try to outline how this algorithm works and how it is related to this affected or unaffected dichotomy. Okay? All right. So here is my test set A. And here is my group G sub A, which is that subgroup of A which fixes this set pointwise, so for which I have a homomorphism that is a giant to this. Okay? Now,
Pointwise.
I'm sorry?
Pointwise, sir. Pointwise.
No. This is a group homomorphism. So G is my ambient group. Yep. G sub A is the setwise stabilizer of A. Setwise. So it fixes this A, because the thing that I am really trying to observe is what's happening inside that set. So, so I look at this, and I have this giant homomorphism here, and I call this, okay, so this is something that completely ignores the input. I didn't even look at the input. I only looked at G. But now I am beginning to look at the input. The first set of pieces of input that I am looking at is the elements that are affected by this homomorphism. This is a giant homomorphism. And I'm sorry, I called it, let me call it C sub A, in fact. This is not phi. Phi is the homomorphism from the entire group, and now I have a different thing, because after mapping to the symmetric group on gamma, I restrict to A. So I simply take no notice of what's happening outside A. So I look at this, and then I look at the set of points affected by this, in the sense defined here. Okay? So I have a giant homomorphism here. There are lots of orbits. Okay? The group G was transitive here, but now I have a much smaller group, G sub A. I have lots of orbits. Some points are affected, some points are not. At least one point is affected. Okay, so I take these elements that are affected. Okay? So it is going to be a growth process. I call it, okay, all right. So this is while something is true, then I start with W being the empty set. W is the part of the input that I am considering. So initially, I am not considering any part of the input. But now, I look at the affected set of what? Okay, so the set affected by the automorphism group with respect to G sub A of my string restricted to the previous window. Okay, so this is the window, which is initially the empty set. So initially, this thing is simply just the group G sub A. But then this becomes everything that is affected by that. So that's my first layer here. But then I repeat this. I have some termination conditions, which I am going to tell in a minute. But until such time, I can repeat this. As soon as I cannot repeat it, I will have terminated. So when can I not repeat it? If this is no longer a giant homomorphism, I will have a current group. The group always goes down. So I have this definition H sub W. Okay, no, it doesn't matter. It's just this group, the automorphism group restricted to W. Okay. Now, once I change W, I will have to recompute this. So recompute the automorphism group with respect to W. That means more inputs are now taken into account. And I will have to justify why can I compute that. Okay? But let's accept that for the moment. And so this is what I keep doing. Okay? So that means that I get the next layer of the beard. I'm growing the beard. So this algorithm, that's what it does. It grows the beard. Okay, the termination conditions is one of two things. Either, the beard grows, more and more input is taken into account, the automorphism group keeps shrinking. At some point, I may reach an automorphism group that is no longer mapping on a giant inside the symmetric group of A. Okay? That's a termination. So termination, so while this CAW is a giant, so by this I mean that I take input on W into account, and the beard is growing. Okay, so this thing is bigger than this. So let me call it this way. The beard is growing. So more points are affected than those that are currently in the beard. So again, what do I do? The next layer of the beard is all the points that are affected by the automorphism group of the previous layers of the group of the beard. Okay? So then I add this additional layer, but it is possible that at some point this thing terminates. I still have a giant homomorphism from the automorphism group of these layers, but it doesn't grow anymore. Nothing else is affected. So let's see, what do I have at this point? At this point, I have partial automorphisms. I have automorphisms of the string restricted to the beard. Okay? But I want global automorphisms. I want automorphisms that extend to the entire set. Okay, so the complement of this set is U. That's the unaffected set. And now, okay, so bear with me again. I am having automorphisms that respect the input on this set. So if one of them takes this point to this point, then that means that if a letter, I don't know, a letter Z was here, then a letter Z must be here, okay? It has to be an automorphism. It has to respect those letters. But I have no idea what is happening outside here. But then what do? I have this group, I have this current group, the automorphism group of X with respect to the current window, and I simply stabilize all the non-affected vertices, all of them. So I fix these points. These are not going to move. Okay, the group is reduced, but it's still a giant homomorphism. So even this reduced group maps onto the symmetric group or the alternating group on A. My claim is that this group is already a subgroup of the global automorphism group of X. This already respects the input everywhere. Of course, it respects the input in the beard, because that's how I made it. But these points don't move, so they can't destroy anything. If a point is fixed, then of course the letter there is respected. Not respected means that I move that position to another position where a different letter stands. If I don't move it, I can't not respect it. So all of a sudden, by this lemma, I got a rich family of global automorphisms. John.
I'm slightly confused. Okay, you're only looking at automorphisms which respect the things in the window at every step, or automorphisms which respect the entire beard?
The beard, the entire beard. Yeah.
So but I'm only looking at aught G sub A in W there?
That's the beard. That's the beard, okay? So, all right, so if this is my old W, then I add this, then this becomes the new W, okay? So the new W is constructed from a group that only respects the old W.
I see. So in every case, W is a superset of the old W.
Yes. The beard keeps growing. Yes.
Is that obvious that it should be a superset?
Okay, I can say two things for that. One of the things is that yes, but the other thing is that, oh, doesn't matter, then let's just add it on. Okay? Either statement would work. So, okay. All right. The trick is, why can I recompute this group? Why can I recompute? That's because of the affected orbit lemma. These orbits are affected, and therefore, when I fix everything here, okay, that's individualization of a polylog number of points. That I can afford. Then this breaks into orbit, which means an equipartition. Oh, that's fine. Okay, then I have much smaller things now to deal with, and Lux's recurrence works like magic. Okay, so that's why I am able to recompute this group. Now, there are two possible reasons for terminating. Either the beard stops growing, but it's still a giant homomorphism. In that case, I get certificate of fullness. If it stops growing because it's no longer a giant, then I got an effective smaller subgroup, and it is an invariant of this algorithm that whatever group I get as the image here, it is always encasing the automorphism group of a full string. Well, an automorphism group of a partial string always contains the automorphism group of the entire thing, as long as that partial string was, of course, invariant, which it is by this process. So this is the growing the beard algorithm. Let me mention that this lemma, oops, where is it? Yes, this lemma also has a name. I call this the design lemma. the design lemma is how I reduce a k-ary relational structure to a graph, a canonical graph. And I call it design lemma because actually block designs come up in the proof. Even Fisher's inequality is used. So this is also going to be 2 weeks from now. Here, I didn't give you all the group theoretic details, but most, and the core ones I did. What I did not say is how to aggregate this k choose t squared times 2 pieces of information, both positive and negative certificates. And let me say maybe a couple of words about that. I actually already said, sort of, what I do with the negative certificates. So if the negative certificates are all over the place, then I am fine. All the negative certificates. So if I have a negative certificate on every test set, then I have an invariant relation, and I use the design lemma. What happens if I have positive certificates? Now, so I will be going to look for this group. F is the group generated by all the positive certificates. Okay? So all the positive certificates generate a group. This is a subgroup of the automorphism group of X. Okay? So I look at that group, and if that group is large, okay, so if in many cases I got a positive certificate, it doesn't even have to be overwhelming, just many in some way, then the group has structure, and I take advantage of that structure. So for instance, if this group already, okay, so this is gamma here, and I look at the support of this group when I project it. I look at F to the gamma, that's the projection of F to this symmetric group on gamma. So, okay, so phi maps F to this thing that I denote by F to the gamma. So that's the action of F on gamma. That has a support, okay? Support is all the points that actually can move. So it has 2 parts. Let me call this the desert. That's where nothing moves. And this is where things actually do move, okay? Now, if this partition into desert and non-desert is a good partition, oh, that's a good coloring, then I am fine. So if the desert is, say, less than half, then I can ignore that, okay? So then I just simply reduce, Lux reduction goes down to the half size problem with the desert, and then the other half size where I don't have the desert, but it's also half, okay? Now, if instead of half, I have much more than half, and much more than half, but I have a good group here. Now that group has a structure. So for instance, if that group is intransitive, then I already have a canonical partition. If that group is imprimitive, transitive but imprimitive, then I don't have a canonical relation, but there are so few domains of imprimitivity to choose from that, again, I can just individualize one set of imprimitivity, and then I have an invariant relation. Then I have a graph. If it is it is primitive, but not simply primitive, okay, then it's doubly transitive, and there is a beautiful 19th century piece of group theory that will prove for me that that simply cannot happen unless the entire thing is all the symmetric group. But if it is all the symmetric group, then I verify that this entire symmetric group here actually occurs. And that has an effect very similar to the effect when I said that I already determined that the entire group is fine. Namely, what happens is that in that case, if there is an isomorphism between X and Y, and both of them have the entire symmetric group action here, that means that I can actually prescribe how I match up the points of gamma between X and Y. So for instance, I can say I fix all of them, and they should still be isomorphic. But if I fix all of them, then I am down to the kernel of that homomorphism, and that's fine. That chops up the domain omega so that I have a good recurrence for Lux's algorithm. So in all cases then, okay, I quickly ran through the hierarchy of various types of permutation groups, which you can find in this book if you like, or ask me afterwards, and that helps me finish this thing up. So back to the thing. The core is finding these local certificates, okay? And so I hope that I gave an idea of that, and thank you.
Questions?
So the Splitter-Johnson conditions, they not only need to hold, but they need to be efficiently testable. Is that correct?
So there will be a quasi-polynomial time algorithm that finds them. Okay, so to be more precise, the algorithm takes quasi-polynomial time and it will incur a quasi-polynomial multiplicative cost. Okay, and that's how we find those structures. Yeah.
Even looking for the large Johnson graph, that seems the hard part, right? Or is
Somehow I am not looking for it. It just pops up. Okay, so there are, I don't know, 24 cases, and in one case, a Johnson graph comes up. It comes immediately labeled. Okay, you could ask, all right, how do I recognize the Johnson graph? I won't spend time recognizing it. It comes labeled. It will say, I am a Johnson graph, here is my labeling.
One question. In the case if there is an X which is, let's say, not affected, which is less affected by a homomorphism phi, can it still happen that there is some other homomorphism which is giant, which it sort of maps the stabilizer of X to the symmetrical?
Well, okay, so the question really is this set gamma unique? Okay, so I have a group. Could it have a giant homomorphism on some gamma and another giant homomorphism on another gamma, and then the same point X could be affected by one of them and could be not affected by the other? And yes, this is perfectly possible. I mean, just take 2 copies of this thing and take the direct product, okay? And then if you take a point xy, which is affected by one and not affected the other, so that point in the Cartesian product is going to be affected by one of them and not affected by the other. But the point is that Lax's algorithm doesn't require for me to find a unique gamma and a unique homomorphism. Wherever I find in G this gamma, then I can work with that.
More questions?
Yeah. Okay. Tim?
So how could this algorithm actually be implemented? Could you program it?
Yeah. Okay. So that's a very good question, and so let me clarify the purpose of this entire enterprise. This is a purely theoretical enterprise. For all practical purposes, graph isomorphism is very well solved. There are algorithms and ever better algorithms. So Brendan McKay and Piperno have come up with an algorithm that is extremely difficult to challenge. And I mean, they are trying themselves to challenge it, and it is very difficult to find examples. So the problem with graph isomorphism is that we don't have benchmarks. Benchmarks would be somehow sets of graphs where the problem is difficult, and we don't know if there are any. Now, I would say that this is one step towards showing that maybe there are none. At least there are none in the sense that we previously thought. We previously thought there might be exponential difficult instances. I mean, if there is no gap in this proof, then they don't exist. But maybe one can go further and prove that one can go further down, but maybe not. Maybe somehow we are reaching a limit, and there will be cases that are at least quasi-polynomially difficult. So that we don't know. And there is this huge collection of potential graphs which are, I mean, the question is there anything difficult lurking there? And so that's what we are probing. So this is worst case analysis, and for practical purposes, there is no point in programming it. But in principle, it would be possible to program it. And then I would still not know how to test the program. Because for the test, one has to bring up some instances that are...
What your instances are there? You take Johnson graph.
You randomly permute it and you try to feed it to the algorithm.
Okay, all right. So if somebody is willing to program it, then we can try. Yes?
And what stops this at quasi-polynomial is that lower bound on m, right? The lower bound on m of 2 plus log n.
Okay, so this is a recurrence. So the recurrence peters out somewhere. And so I have a limit on m below which these things don't work. For instance, this doesn't work, okay? But there are parts of the split or Johnson routine that stop working already at log cubed n. So I stop it there.
Right, more questions. All right, let's thank the speaker again.